As a robotist, one of my long-time dreams is to develop fully autonomous system that can perform intelligent action without human intervention. I envision a future where fully autonomous car will dominate the roads. Nonetheless, I wonder how this technology will impact our life. So, when I was pursuing my postdoctoral training at Nagoya University, my research aim was to answer these questions. How do you judge the quality, the real autonomous nature of a car? Since self-driving cars are becoming closer and closer to becoming reality, a crucial question is to ask how to detect anomalies for autonomous driving. So today, I'm going to talk about anomaly detection for autonomous driving. This is a joint work between myself and my colleagues Chiyomi Miyajima, Kazuha Takeda, and they are from Nagoya University. So anomaly detection is the process of identifying unusual patterns that do not conform to expected behavior. Typically, items or events in datasets differ from the norm based on two basic assumptions. So anomalies only occurs very rarely in the data. Second, their features differ from the normal instance significantly. If you look at this figure, I would say 99% of you people will say the red fish is the anomalous here, but 1% of the population is still argue. So in that context, they will be anomalous. So the anomaly detection problem has been widely studied in computer science literature. Earlier, anomaly detection system is envisioned as a personal software assistant that helps monitor a user account for penetration. However, today we have seen a lot of applications for the anomaly detection, including fraud detection, intrusion detection, system health monitoring, and today I'll be talking about the behavior anomalies. So before getting it started, it is important to establish some boundaries on the definition of anomalies. Anomaly can be broadly categorized into three categories: point anomaly, contextual anomalies, and collective anomaly. So if the specific value within the dataset is anomalous with respect to the complete data, then it is known as a point anomaly. For example, the earlier bank fraud example that I have mentioned is a point anomaly. On the other hand, if the occurrence of a data is anomalous for a specific circumstance, then it is known as contextual anomaly. For example, the anomaly occurs at a specific interval of a period. Especially if you talk about the driving anomaly, it is a contextual anomaly. And the collective anomaly is the combination between the point anomaly and contextual anomaly. And if the collection of the occurrence of the data is anomalous with respect to the rest of the data set, then it is known as collective anomalies. For example, in medical signal processing, we see the breaking the trend of observed ECG signal is collective anomaly. So in the realm of signal processing, driving behavior analysis, anomalies are inconsistent driving behavior, which may lead to a road accident. Since the driving behavior can be modeled as a multidimensional time series data, this type of anomalies are referred as contextual anomalies. We are interested in an effective anomaly identification in driving behavior, which is one of the crucial steps for ensuring safe driving. So detecting driving behavior anomalies is useful in multiple contexts. For example, driving school teacher could understand the driving behavior of his students intuitively by detecting anomalies in the students' driving behavior. In addition, security and police officer at a transportation company could monitor the driving behavior of a taxi or bus driver remotely by the anomaly score, and thus they may inform a driver promptly when a dangerous driving behavior is detected. Likewise, we expect that the anomaly detection of driving behavior would be useful for accident investigation. Since the anomaly detection of driving behavior can allow investigators to determine which unusual driving behavior had led to an accident, it would be very useful for the car insurance company to calculate their premium rate. Thus, for the next generation transportation system, an effective anomaly detection method of driving behavior will be useful for developing various support systems for monitoring, reviewing, and analyzing driving behavior and driving assistance systems. In particular, the advent of autonomous driving technology would lead to a transportation system with mixed manned and unmanned traffic vehicles for which an automatically identify the common anomalies in human driving behavior will be a crucial safety requirement. So enough of this introduction of anomaly. Let's get into the algorithm that we really care about. So an anomaly detection algorithm should either label each time point with anomaly or not anomaly, or forecast a signal for some point and test if this point value varies from the forecasted enough to deem it as an anomaly. Most of the technique that we can find in literature can be divided into two categories. One is statistical method, another one is machine learning based approach. In a statistical method, identify irregularities in data is to flag the data points that deviated from the common statistical properties of a distribution, including mean, median, mode, quantiles. On the other hand, the machine learning-based approach typically learns normal behavior from the dataset and then it tunes itself to identify abnormalities that fall outside the learned region. In many cases, each dimension of time series data is not independent of each other in a statistical sense. For example, accelerator opening rate and longitudinal acceleration are mutually dependent. We can then hypothesize that only a small number of hidden features that are essential for visualizing driving behavior from the high-dimensional multivariate driving behavior data. In 2007, our former colleague Liu et al. Proposed a driving behavior visualization method which focuses on extracting essential hidden features from measured redundant driving behavior data. Particularly, they proposed a visualization method that utilized a deep sparse autoencoder to extract low-dimensional hidden features from high-dimensional time series data. For instance, we have 9-dimensional driving behavior data. After winding this 9-dimensional driving behavior data, we have 90-dimensional driving behavior input vector. Second, then we use the encoder from the deep sparse autoencoder to map this 90-dimensional input vector to 3-dimensional RGB space. Then finally, using the decoder, we reconstruct this 3-dimensional RGB space to the 90-dimensional driving behavior data. And we done this unsupervisedly, and thus we learn the driving behavior first, and then we can assign a specific color for a specific driving behavior pattern. For example, sky blue for high speed forward, deep pink for turning right with accelerate, and green is turning left with accelerate. So, and so on. Now that we have basic understanding how we can visualize our driving behavior, now let's talk about how we can utilize human expertise to determine whether something is anomalous or not. So for this example, let's focus on this rectangle. This is the highway driving behavior, and our expected behavior from this context is high speed forward or accelerating forward. And if you can observe some different color that represent stopping vehicle, right rear reversing, left rear reversing, those color in that context, it would be anomalous for us. So our target is to automate this process because human has a lot of prior knowledge, but we want machine to do that. And in order to do that, we develop deep learning-based anomaly detection methods that can automatically identify the common anomalies in human driving behavior by fusing multimodal sensor data to learn normal driving behavior first and then detect the anomalous behavior during the testing. So to learn useful driving behavior from the real data, we need a lot of positive and negative example. In real world, it is difficult to obtain anomalous driving data due to their confidential nature. So therefore, I'll talk about a little bit how to generate realistic synthetic anomalous driving data using a network called generative adversarial neural net. So let's move on to the multidimensional sensor data processing first. For autonomous car, it is essential to have a clear view and understanding of their surroundings to be able to navigate safely. To generate this view out of many sensors, we are interested in to use LiDAR sensor, front camera, and canvas data. So each sensor has its own pros and cons. For instance, the LiDAR is mostly invariant to all weather and lighting conditions, but lacks in rich class of information like RGB camera. On the other hand, driving behavior can be measured using a various type of sensor connected to the control area network, aka CAN. The measured multidimensional time series data are called driving behavior data, and we rely on the canvas that capture the driving behavior of an agent using multi-modal sensor output. To be able to learn the driving behavior of an agent, it is necessary to synchronize the data delivered by these sensors so that we can process them for the neural networks. Speaking of synchronization, each sensor has own frequency for detection and extraction of the scene information. CAN sensors are faster in response but noisy, while LiDAR is accurate but slower, both of which have their own pros and cons. The synchronization of the data should ensure a high certainty about the existence of perception and action. And for that, we need to have a common representation of all sensors so that our neural network can use those sensor information effectively. So that's why we have defined we convert this CAN image and the three-dimensional point cloud data to image format, and so that our neural network can easily use those sensor information and learn the naturalistic driving behavior. And to do that, for example, in CAN, we have 16-dimensional data signal channels, and we assign 100 buffer length for each channel based on the time synchronization. And when data index overflow, the buffer size, it is inserted at the very beginning. Thus, we recursively update the buffer to synchronize with the depth image. So the reason we synchronize with the depth image, because in our setup, the LiDAR is the slowest sensor that we have. It operates at 10 hertz. And then we synchronize all the images with respect to the LiDAR so that we have a nice driving behavior representation. On the other hand, the LiDAR provides you three-dimensional point cloud data, which requires huge memory to process and the computation power. And then we were thinking about how we can use this three-dimensional information in two-dimensional space, and we have done by converting this LiDAR three-dimensional point data to the two-dimensional depth image. So basically, we convert this LiDAR three-dimensional point cloud data to two-dimensional depth image that is easier for neural network to process. So as I mentioned earlier, in real world, it is very difficult to obtain anomalous driving dataset because accident occurs very rarely in contrast to the normal driving behavior. And when it happens, sometimes accident damage all of your devices, so you may lose your recording devices. And finally, and the most importantly, due to their confidential nature, accident reports are not available publicly. So we are interested in generating synthetic anomalous driving data using generative adversarial neural network. So before getting into our proposed networks, let's talk about how to process data that can be used for anomaly detection method. And for this, we have conducted a small experiment in our lab setup in order to determine the risk while changing lane in a highway environment. For this setting, we are given a pre-recorded observation of the driving behavior data while traveling along some paths. For instance, when a driver with an index I along a path, we record his behavior in continuous time with multidimensional time series data. In our data, all the sensor information has synchronized and annotated with a human expertise for each frame. And to this end, we want to recognize distinctive anomalous behavior in continuous driving behavior data. And to simplify this problem, we use a fixed length time sequence for representing the driving behaviors. Thus, by partitioning the continuous driving behavior dataset into a discrete observation, we want to solve the continuous detection of risks in the lane changing behavior. So since it is hard to get an optimal decision boundary of a neural network with a positive example only, our goal is to generate anomalous synthetic data that mimic the real driving behaviors. So by concurrently training a generative model and a discriminative model on the naturalistic driving data, we are able to learn the naturalistic driving behavior pattern. The key idea is to use a parameterized generative model to produce a driving sequence, while a parameterized discriminative model provides a guidance for improving the generator performance. During adversarial training, the generator improves in generating naturalistic driving sequence, and the discriminative progress in correctly identify real and generated driving sequence. By feeding the reconstructing class information to the discriminator, the basic generative adversarial network framework is augmented for auxiliary classification tasks. To sample from the generator, so we first define a low-dimensional latent space, which is one-dimensional random vector uniformly distributed over a fixed distribution, and then we sample from the latent space with an associated class to generate a fixed length driving sequence. So then we evaluate this network with the other networks that, for example, we have convolutional neural net, multilayer perceptrons, and the vanilla GAN. And we have seen that for the discriminative task, CNN outperforms the AC GANs. But it doesn't learn to generate negative example, which in our case is anomalous driving data. Therefore, we are interested in ACGAN, which has moderate performance, but it learns how to generate synthetic anomalous driving data. So we are also interested in investigating minimal of sensor information to detect anomalies. Therefore, we proposed several neural networks that consider three types of sensor information, primarily surrounding environment, driving data, and history of driving data, and so on. So let's talk about the sensor architecture, so the network architecture. So we have first convolutional neural network. First, we have a depth image, and we perform a series of convolutional operation over this depth image to come up with the behavior data that is a CAN image. So we have an input as a depth image, output as a CAN image, which represent your driving behavior. And this training has done in supervised fashion. On the other hand, on autoencoder, we have this luxury to incorporate multiple sensor information. For example, we have this depth image, and we also can incorporate the CAN information in here, and then we learn jointly from those two information using an autoencoder architecture. First, we convert them to a common 16 times 1 layer, and then we concatenate these two layers, and then we decode this layer to reconstruct this depth image and the CAN image again. And by doing this, we learn how to which parameters, which features are important to identify the driving behavior. And lastly, we have a CNN RNN, which takes care of the sequence of information. Actually, in this network, we have all sort of sensor information. That we have depth information, we have CAN image, we also have camera image, and we fuse all these sensor information using a merge layer, we call it shared layer, and then we learn from this shared layer by fusing all this sensor information, what would be the next behavior for the drivers for a particular instance. So let's talk about the experiment and evaluation. So as I mentioned earlier, neural networks requires both positive and negative example to learn behavior effectively. To remind you again, we have this data set collected by the Behavior Signal Processing Lab from Nagoya University. On the other hand, we have generated synthetic anomalous data using the ACGAN architecture that I have mentioned earlier. And then we train three deep neural networks that I mentioned earlier to learn the naturalistic driving behavior data. And let's see how the network learns the naturalistic driving behaviors, whether they can learn it or not. So here you can see a demonstration. I don't know. I normally do not have luck on playing video. Yeah, okay. So here you can see a demonstration how the CovNet learns the naturalistic driving behavior. So as you can see, the performance of the CovNet is very bad because it only cares about the depth information. So the expected behavior is that high speed forward and accelerating forward, and the red line and the pink line, when they align on each other, that means that is accelerating forward, right? That is our expected behavior. And by no means this is this network can tell us the naturalistic behavior in this particular sense. Moving on to the next autoencoder, here we see a little bit nice performance because autoencoder take care of the CAN image as well as the depth information together, and actually it tried to compute the driving sequence as well. But the best performance we have found so far is by CNN GRU network, the RNN, when we think about fusing all type of sensor information. For example, we have this CAN information right here, and we also have the depth camera information, LiDAR information right here. and we also have this front camera information right here. And when you fuse all this sequence information to learn the naturalistic behavior, the network eventually learn it. So for example, the first zigzags means that those are the not high speed, and when the network align to the two lines align to each other, that means it is the expected behavior. For this context, the high speed forward and accelerating forward is our expected behavior. Look at this. Here is the driver is turning, so this is no way it could be an expected behavior because it's turning left and braking the paddle. So that's how we can tell. The network can automatically tell, well, this is not the expected behavior that we are looking for in this driving sequence. So now we can define a multiple behaviors, and we can run this experiment over and over again to demonstrate that actually a network learns each of the behaviors. And once the network learns each of the driving behaviors, what we can do, we can actually use this information to predict whether our behavior is anomalous or not. Let me explain how. First, we have this actual driving behavior data from this our multimodal sensors that we have CAN image, we have depth image, and we also have the front camera image information. So we feed this information to our neural network, and the neural network come up with the expected behavior for the driver, which in this in previous case it was the human score. So in here we don't have any human score. Instead we have a prediction from the neural network, and those information is fed to the anomaly detection module. Then anomaly detection module compare your actual driving behavior and the expected prediction from the neural network and conclude whether this behavior is anomalous or not. And if you're working on the machine learning area, what is very important is to look at the graph, right? So this is all we have in machine learning. As you can see that this is a ROC chart that represent the performance of the network as expected. Obvious, when you're training the network only using the depth information and trying to predict the behavior information, the network has huge loss. And when you're adding more information like depth information, CAN information, and image information, your network actually learn better than expected. Then in the performance, during the ROC curve, we have seen that the autoencoder has reasonable performance, but CNN is the worst one. And the best performance that we have got so far is from the CNN GRU architecture. It has overall 80% of ROC curve. So to remind you my work that I have done in Nagoya University, basically we are focusing on to learning the normal human driving behavior first, and then trying to detect the anomalous driving behavior. And for that purposes, we use 3 deep neural network to detect the anomaly, and we train them in such a way by fusing the multimodal sensor information, and we fuse those information with the different network architectures. And we have this problem that we do not have a lot of anomalous data. So I also talk about a little bit of how we can generate synthetic anomalous data by using a generative adversarial neural network. Thank you for listening, and that's all for today, and I will be taking questions from here. Thank you.
Thank you so much.